Welcome back to Differential Equations. In this lecture, we're going to turn our attention to learning about second-order ODEs. All right, so think of this as our kind of transition from first-order ODEs to second-order ODEs. We're still going to need some of our first-order ideas, so always keep in the back of your mind the types of first-order differential equations. They could be separable, homogeneous, exact, or linear. Those are the four main categories that we learned how to solve. Now, when we transition to second-order ODEs, some things change, and in general, the mathematics gets a little simpler. There was a lot of different techniques for first-order ODEs, some complicated integrations. That generally goes away and gets replaced with more algebra, as we'll see later in this lecture. All right, so what I want to do right from the beginning is introduce the main type of second-order ODE that we'll be focusing on for the remainder of our course primarily. So this is a second-order linear ODE. It has the same general form almost as a first-order linear equation, but we're adding in a y double prime term. All right, now some things to point out that make this linear. Y and its derivatives are raised only to first powers, and y, y prime, and y double prime are only multiplied by functions of x. Notice in that general form, a2 of x, a1 of x, and a sub 0 of x, those are all functions of x multiplying y and its derivatives. All right, now these are just some basic things you can notice for what makes a second-order ODE linear, but still this doesn't tell us the importance of linearity, which we'll be getting to very shortly in this lecture. All right, so let's just introduce some examples of second-order linear ODEs. This was one we saw back in our introduction that is incredibly important. There's a lot of topics that are going to be motivated by this differential equation. Now, before we even move on, just think, can you find solutions to this differential equation? Pause if needed, rewrite the differential equation. We did this earlier. See if you can find those solutions. All right, so if we rewrite this, subtract the y to the right-hand side, our two solutions, which we, again, pointed out in our introduction to our course, the two solutions are sine of x and cosine of x. Now, the main change from first-order to second-order ODEs is second-order differential equations have two solutions. And we're going to have to kind of be a little bit careful with how we define what two solutions mean, but I'll say very informally right now, second-order differential equations have two different solutions. And I think by all basic ideas that you know, sine of x and cosine of x are different. We're going to make that idea of functions being different more precise later in this lecture with something called linear independent functions. All right, let's take a look at just some other examples here, B, C, and D. We're not going to attempt to solve these, but that's what we'll be getting through in the next few lectures over the next few weeks. All right, worth pointing out, they're all linear and they're all second order. Notice the last one, example D, y and its derivatives are being multiplied by simple functions of x, which is multiplying y prime, and x squared, which is multiplying y double prime. All right, as we go throughout this second part of our course, we're going to introduce the techniques we need to be able to solve these second-order ODEs. All right, now before we move on, I want to point out that there are currently certain special types of second-order ODEs that we actually have the tools to solve. Now, here's a very simple one. It is a second-order ODE where there is only a second derivative term. So notice here, there's only y double prime. There is no y prime or y term on that left side or anywhere in that differential equation. Now we actually introduced this kind of as a preview question on homework number 1. We basically can solve this by integrating twice. So if you look at an example, y double prime equals 24x squared, integrate that twice, and we get this as our solution for y. Each integration introduces a second constant. And since we integrate twice, we get 2 constants here, C1 and C2. Earlier in the course, we might have used C and D for our constants, but we'll change notation and use primarily C1 and C2, or more properly, C sub 1 and C sub 2 for our constants. All right, let's introduce a second type of second order differential equation that we can solve. And this one looks certainly a lot more complicated. Now what's special about this one, the first example above, the differential equation only contains y double prime. This one, it contains y double prime and y prime, but notice there is no y term in that differential equation. What makes this special is with a trick, a certain kind of algebraic substitution, I'll say, we can actually convert this second order ODE into a first order ODE. And this is a method that is known as reduction of order. And this will reduce, again, a second order ODE down to a first order ODE. Why is that of benefit? Well, we have a lot of methods to solve first order ODEs. So one of the oldest tricks in the mathematical handbook, take a problem that you can't solve and turn it into one that you can. And with this technique called reduction of order, we can turn this second order ODE into a first order ODE. Now the reduction of order substitution is actually really simple. We're just going to substitute, sometimes it's called a change of variables. We change y prime to some function z. All right, and with that, if z equals y prime, differentiate that, z prime equals y double prime. If you plug that into your differential equation for y, what we now get is a first order differential equation for z. So at this point, once you use this reduction of order trick, you get a differential equation that you can solve. All right, so let's keep going. Take a look at a specific example. This is a good one. Maybe you'd like to try it. So if you're up for it, pause and try implementing this reduction of order trick. We'll check in a few minutes if you want. If not, just wait and continue on. All right, in case you didn't want to try this, let's go through it. We make this substitution or change of variables. We're going to say y prime equals some function z, which then means z prime equals y double prime. If you plug that into the differential equation for y, it converts to this first order ODE, z prime plus 2z equals 0. Now this one can be solved very quickly, either as a separable ODE or as a linear ODE. Notice the p of x, it's not multiplying y anymore, but multiplying z. The p of x would just be 2, which would lead to a very simple integrating factor. All right, and if you solve that differential equation, again, it's first order. So at this point in the course, you should feel comfortable solving that differential equation for z. And you should find z equals a constant times e to the negative 2x. All right, now that solves the differential equation for z, and we need to kind of wind our way back to getting a solution for y. So now we back substitute z as y prime. And the main theme for our course, how do you undo a derivative? Integrate. So you should find here that your y comes out to a constant times e to the negative 2x plus another constant. Just be careful with that integration of e to the negative 2x. The integral gives you a factor of negative 1/2, and we're just absorbing that into the constant c1. A constant times negative 1/2 is another constant. All right, so at this point, we currently know two different types of second order ODEs that we can solve. What we're going to be transitioning to in the next few lectures is, well, what if we, for instance, in the second example there, where there is no y term, what if there is a y term? That's what we'll be learning about over the next few lectures. All right, now with those two types out of the way, I feel like this is a good point in our course to go into detail about the importance of linearity. Linearity is really not that important for first order ODEs. It has a particular significance for second order ODEs though, which we're going to go into detail right now. All right, so what we're going to look at are two examples of differential equations. On the left, we have a linear ODE, y double prime plus y equals 0. We already know what those solutions are, sine of x and cosine of x. And then we're going to compare that on the right with this nonlinear ODE, y double prime plus y squared equals 0. And just be careful with the notation. Y squared, that's raising y to a second power. The y squared term makes that nonlinear. All right, now what we're going to pretend to see the importance of linearity, we're going to pretend we already know two solutions. Now, the linear ODE, we do know two solutions, sine of x and cosine of x. But let's forget about that. Let's just suppose y1 and y2 are solutions to that linear ODE. And we'll kind of do the same thing for the nonlinear ODE. So what that means is individually, if we plug y1 and y2 into their respective differential equations, since they're solutions, they should satisfy the equation. All right, so that's kind of our assumption. We're going to assume y1 and y2 are solutions to the linear ODE, and then a different y1 and y2 solutions to the nonlinear ODE. All right, and the question we're going to ask, which gets to the heart of why linearity is important to second order ODEs, the question is, if y1 and y2 are solutions, is their combination a linear combination, y1 plus y2, is that also a solution? So the answer is either yes or no, and we're going to go into detail about checking that right now. All right, so let's first start with the linear ODE. Again, we know what the solutions are. y1 equals sine of x, and y2 equals cosine of x. Forget about that, and try to be comfortable with the abstract notation of y1 and y2 just being solutions. All right, what does that mean? Well, when you plug y1 and y2 into the differential equation, they satisfy it. What we're asking right now is the question, is y1 plus y2 also a solution? If we want to be a little more technical, we would say if we have two solutions, y1 and y2, is a linear combination of them also a solution? All right, so let's check. We're going to be replacing y everywhere in the differential equation with y1 plus y2. All right, and if you just be careful with your derivatives and parentheses, we get to here. Notice in the first term, because we are adding y1 and y2, we can just successively differentiate each term. If we were multiplying y1 and y2 in those parentheses for the first term, then we'd have to use the product rule. So this is just pretty straightforward here, differentiating each term. And what we're going to do now is use the fact that we are assuming, but we really know, that y1 and y2 are solutions. So let's rearrange this kind of end result. We can rearrange it in this form, and we can see that y1 double prime plus y1, well, since y1 is a solution, we know those two terms add to 0, and likewise for the same two terms for y2 double prime plus y2. y2 is also a solution, so that becomes 0. All right, and if we check, 0 plus 0 gives 0. So the answer here, yes, y1 plus y2 is also a solution here. All right. What this property is known as, in case you have some ideas floating around in your head from exposure to other courses or other ideas, this is known as the principle of superposition. We're going to make that more precise in a little bit with our first kind of theorem for second order ODEs. All right, so what we can see here is for the linear ODE, y1 plus y2 is also a solution. Well, let's kind of go through the same argument, but now for the non-linear ODE. All right, now here, I actually don't know what y1 and y2 would be, but we're just going to pretend or suppose that y1 and y2 individually are solutions. And we're going to ask the question, is there some y1 plus y2 also a solution? Now, if it is a solution, when we plug it into the differential equation, since the right-hand side of that differential equation is 0, we would want to get 0 here for our right-hand side if y1 plus y2 is a solution. All right, so I'd like you to pause here and try to work this out yourself. Maybe give yourself a minute. We'll check in after that, but I want you to at least make an attempt at this. All right, welcome back. The y1 plus y2 double prime, that we can successfully differentiate each term individually, but be careful with the squared term. We have y1 plus y2 squared. That's not a derivative, but we're just expanding that or multiplying that out, foiling, if you will. All right. Now we're going to rearrange here like we did in the linear example a few moments ago. I can rearrange the y1 terms together. I can rearrange the y2 terms together. Since y1 and y2 individually are solutions, those first two grouping of terms each are 0. But notice what we're left with, 2y1 times y2. Now, since that's not 0, or more specifically, it's not identically 0, then that means y1 plus y2 is not a solution. If we got 0 at the end here, y1 plus y2 would be a solution. 0 is the right-hand side of our original nonlinear ODE here. All right, so what we can see from this example is no, a combination of solutions is not also a solution to a nonlinear ODE. So let's go ahead and make that precise with our first kind of theorem or result on second order ODEs. Just to summarize what we went through, y1 plus y2 is a solution to the linear ODE. y1 plus y2 is not a solution to the nonlinear ODE up there. All right, let's go ahead and kind of summarize what these two examples we're getting at. And we have our first theorem, and this is what's known as the principle of superposition. Very important in electronics, electrical engineering, very important to quantum mechanics, but we'll save that for later. All right, and the theorem is very simple. It starts by if y1 and y2 are solutions to the linear ODE, notice the right-hand side there is 0. We're going to kind of be more specific about why that's 0 in the upcoming lectures. All right, if y1 and y2 are solutions to this linear ODE, then a linear combination, a constant times y1 plus a constant times y2, that is also a solution for any pair of constants C1 and C2. All right, in plain language, what this says is if you have two solutions, add them together as a linear combination, you get another solution. All right, now some of the terms that we just talked about, we're going to write down and make precise. C1 times Y1 plus C2 times Y2, that's what we call a linear combination of Y1 and Y2. All right, we're going to refer to the set of solutions, Y1 and Y2. That's going to be referred to as a fundamental set of solutions. And for our previous example, the linear ODE, y double prime plus y equals 0, our solutions, sine of x and cosine of x, form what we're going to call a fundamental set of solutions. Now, if we combine those two solutions, sine of x and cosine of x, what this theorem says is that all solutions to this differential equation have the form a constant times sine of x plus a constant times cosine of x. So in some sense, once you get your two basic solutions, sine of x and cosine of x, you can then build up all other solutions from those two basic solutions. All right, now the question that we're going to ask right now to get us to the next topic is, when do two functions or solutions form a fundamental set of solutions? In linear algebra, for those of you that have taken linear algebra or maybe will be taking it shortly, this is a question that you would have been asked in your course in linear algebra as the question, when do vectors v1, v2 up to v sub n, when do they form a basis for a vector space? Now, some of the notation might look familiar. Instead of C1 times Y1 plus C2 times Y2, here your linear combination might have been a linear combination of those vectors V1 through V sub n. All right, now to get to that question, what it means or how do we determine when a set of functions form a fundamental set of solutions to an ODE, we need to give some precise definitions. For those of you continuing into higher level mathematics, it is very important to keep track of definitions. As we're about to see, one definition is referenced in the next definition, one theorem references another theorem, and it's all just keeping track of definitions, theorems, all sorts of mathematical results. All right, so let's start to prepare you for that with our first definition that we'll give for what it means for a set of functions to be linearly dependent. All right, now this is a precise mathematical definition. What linearly dependent functions are, linearly dependent just means the same. So this is somehow saying multiple functions are really the same. All right, how we define that mathematically here is as follows. We say a set of functions, y1 through y sub n, are linearly dependent if there exist non-zero constants C1 through C sub n such that this linear combination C1 times Y1 plus C2 times Y2 all the way up to adding C sub n times Y sub n equals 0. Now, what in the world does that mean? What this is getting at is that one of the functions in that list, in other words, one of the functions y1 through y sub n, at least one of them can be expressed in terms of the others. Or in other words, one of the functions in that list depends on the others. And what that equation gives us there, that's the way that we're going to be able to express one of these functions in terms of the others. All right, and it's important here to notice it's saying that there exist non-zero constants C1 through C sub n. So they all have to be non-zero. All right, so let's take a look at how that equation plays into this definition. All right, let's just focus on a small number of different functions. Let's say the functions of interest to us are y1, y2, y3, and y4. All right, now if these are linearly dependent, there exists constants C1 through C4 such that this linear combination equals 0. Now what I'd like you to do is take that equation and solve it for y3. Pause, give yourself a minute, go through some pretty simple algebra, and solve for y3. All right, so this should go pretty quick. You can subtract the terms with y1, y2, and y4, and then you can divide by C3. Notice the assumption about the constants being non-zero kicks in. If C3 were 0, then you couldn't divide by it. But since C3 is non-zero, you can divide by a non-zero number. All right, so you should get something that looks like this for y3. And what we have done is now expressed y3 in terms of the other functions in that list, y1, y2, and y4. All right, so that's what we mean when we say a set of functions are linearly dependent. At least one of the functions in that list is a combination where it can be expressed in terms of the others. All right, when you're ready, let's get to our next definition for what it means for two functions to be linearly independent. And this is where the definitions start to reference one another. So for our next definition, we say a set of functions y1 through y sub n are linearly independent if they are not linearly dependent. All right, in essence, what linearly independent functions are, they're functions that are all different. Linearly dependent means the same, linearly independent means different. All right, so let's look at our definition here. What would it mean for a set of functions to be not linearly dependent? So let's go to our linearly dependent definition above. And what would it mean for that not to be true? All right, well, it would just mean in order for that equation to be true, that linear combination of constants times your functions equaling 0, the only way for this to be not linearly dependent would be if all those constants, C1 through C sub n, all equal 0. And what this means is now that none of the functions in that list, y1 through y sub n, can be expressed in terms of the others. That's how we identify those set of functions as all being different. None of them can be expressed in terms of the others. Again, for those of you that have completed linear algebra or will be going to take linear algebra soon, these definitions are very similar to the definitions for linearly dependent vectors and linearly independent vectors. Just replace the word functions with vectors and you get your linear algebra definitions. All right, so let's just summarize here. Again, the definitions are typical of what you see in a mathematics course, higher level mathematics at least. But what they're getting at is linearly dependent means the functions, or some of them, are the same. Linearly independent functions means they are all different. All right, once you're ready, let's take a look at some examples of sets of functions that might be linearly dependent or might be linearly independent. All right, now since we're dealing with second order ODEs, we're mainly concerned with two functions, y1 and y2. And we're going to ask, are these two functions linearly dependent or are they linearly independent? All right, now how we're going to check if this set of two functions is linearly dependent or linearly independent is we're going to try to see if we can find non-zero constants such that if I multiply y1 and y2 by appropriate combinations, I can get their sum to equal 0. So see if you can pause and just look for numbers that you might multiply y1 by and y2 by, such that when you add them, you get 0. There's a lot of different possibilities. See if you can find one. All right, and here's a very simple set of constants. Let's take C1 to be 1 and C2 as -3. And if you multiply C1 by Y1 and C2 by Y2 and then add, you do get 0. And what that means is those two functions, since there exist non-zero constants such that their linear combination is 0, this means those two functions are linearly dependent. All right, let's take a look at a more challenging second example. Let's say as our set of two functions, we have y1 as sine of 2x, and then y2 as sine of x times cosine of x. Now this one is a little trickier, but see if you can find constants to determine if these are linearly dependent, or if no constants exist, they would be linearly independent. We'll check in about a minute. All right, welcome back. Now, if you're having trouble finding two non-zero constants that work, well, let's point out the trick here. It's always good to keep in mind some basic trig identities. And the ones that make a difference here are the double angle identities, specifically the double angle identity for sine of 2x. Sine of 2x equals 2 sine of x times cosine of x. All right, now that makes all the difference here, because now we can rewrite equivalently y1 as 2 times sine of x cosine of x. Now, see if you can pause and find those two non-zero constants. All right, again, there are a lot of different possible sets of constants that work. A simple set here, let's take C1 as -1/2 and then C2 as 1. If you use those two constants, multiply them to y1 and y2 and then add, you do get 0. And that would mean then, since there exist non-zero constants, such that their linear combination equals 0, these two functions are linearly dependent. And again, what that means, if functions are linearly dependent, that means they're basically the same. And here, it was your trig identities that kind of determine that. All right. Now let's advance to a third set of functions here, referring to our motivating linear ODE from the start of this lecture, and actually from the start of our course. Let's suppose we asked the simple question, are sine of x and cosine of x different functions? Are they the same? Are they different? Are they linearly dependent, or are they linearly independent? Pause and see if you can start thinking of some trig identities that might relate them together. All right, welcome back. Now you're probably racking your brain through all those trig identities that you memorized, right? You know all of them, right? That's okay. But there's at least one primary identity that relates sine and cosine together. The basic Pythagorean identity. Now be careful here. Linear combinations were allowed to multiply by constants and add. This Pythagorean identity involves squaring. And think back to your nonlinear ODE from earlier in this lecture. The y squared term made the differential equation nonlinear. All right, what we can do here with your basic Pythagorean identity is express cosine of x in terms of sine of x, or specifically cosine of x in terms of sine squared of x. All right, what I want to point out is while we have achieved that, we've expressed cosine in terms of sine, the combination is not a linear combination due to squaring and here taking a square root. Those are nonlinear operations. So you maybe have thought of this identity, but it doesn't actually work. So maybe there are other trig identities out there that would work, but we just can't think of them. So how would we determine if these two functions are linearly dependent or linearly independent? It'd be really nice if there was a shortcut, right? There is. And this is another theorem that introduces a mathematical quantity called the Wronskian. Now this addresses this question at the top there. How can we determine when a set of functions is linearly independent? There's a very simple test, which this theorem outlines, for how you would determine if a set of functions are linearly independent. All right, and it involves taking those sets of functions, y1, y2, up to y sub n, and putting them in an n by n determinant. All right, so we put in the first row of that matrix or determinant the functions, and as we go down to the next row, we put in the first derivatives, then the second derivatives of each function, and then we finally finish there. Notice since we start with the functions at the top, y1 through y sub n, in the bottom row, we have n minus 1th derivatives, not nth derivatives. All right, so basically first row, we put all the functions, each row below successive derivatives. All right, now there are a lot of complications with calculating determinants of large sizes, but forget about that if you know how to do that. But what this theorem says is if you calculate this determinant for these functions, which we call the Wronskian, if the Wronskian comes out to be non-zero, then those functions y1 through y sub n are linearly independent. Seems really simple, right? Well, the downside to this is as you scale up the size of your determinants, anything beyond, I'll say, a 4x4 determinant is very difficult to calculate, usually requiring special numerical algorithms to do so. All right, fortunately for our purposes, we're dealing with second order ODEs and only 2 functions for our fundamental set of functions y1 and y2. So we're only going to need a 2x2 determinant. All right, so let's use this theorem to go back to our third set of functions, y1 as sine of x and y2 as cosine of x. Now it'll be very straightforward with our theorem using the Wronskian to determine if those 2 functions are linearly independent. All right, off to the right there, we have the simple formula for a 2x2 determinant. Comes out with your entries there, A, B, C, and D, arranged in those rows and columns. The determinant is basically the difference of the diagonals, or the product of the diagonals, AD minus BC. All right, if we calculate the Wronskian for these 2 functions, in our 2x2 determinant, we put the functions sine of x and cosine of x in the first row, and then below, we put their derivatives. All right, and if you calculate this 2x2 determinant and factor out a negative, apply your Pythagorean identity, you get that the Wronskian comes out to equal -1. Now, what does this tell us from our theorem? Well, -1 is not 0, which means these functions are linearly independent. Now, maybe you were intimidated with trying to calculate an n by n determinant, but for our course, we're only going to need this 2x2 determinant version, since we're only dealing with, for a second order ODE, 2 linearly independent solutions. This result using the Wronskian is something that we'll reference throughout the rest of the course, so make sure you try to understand it now. We'll be throwing that in through the next part of this lecture when we get to a lot of examples.